Welcome, students. In this explainer created by MindSticks Foundation Trust, we're going to dive deep into the core principles of gravitational physics. We'll be tracing the journey from the fundamental mathematics of circular motion all the way to figuring out exactly how and why Earth's acceleration varies. It's a fantastic journey of logic and physics, so let's get right into it. Here is our agenda for today. We'll be systematically moving through 6 key topics, starting off with centripetal force, then gravity between everyday objects, the physics behind ocean tides, Earth's gravitational pull, calculating acceleration, and finally, exploring why gravity actually varies slightly. All right, let's start with section 1, centripetal force and Newton. So, think about an object moving in a circle with a constant speed, like a planet orbiting the sun. This steady, circular motion is only really possible because there's a constant force pulling that object directly towards the center of the circle. We call this the centripetal force, and mathematically, it's quite elegant. If m is the mass, v is the speed, and r is the radius of the path, the magnitude of this force is simply calculated as F equals mv squared divided by r. Now, how did Newton actually deduce the inverse square dependence in his famous law of gravitation? Well, he used Kepler's third law to help him out. First, he expressed the planet's speed as the distance traveled, the orbit's perimeter, 2 pi r, divided by the time taken, or the period of revolution, t. When you substitute that velocity into our centripetal force equation, and then do a clever little mathematical trick of multiplying and dividing by r squared, you can neatly bring in Kepler's third law, where t squared over r cubed is a constant, k. By doing this, Newton mathematically proved that the force is inversely proportional to the square of the distance. And there you have it, the famous inverse square law. Moving right along to section 2, gravity between everyday objects. Now, I want you to think about this question for a moment. Newton's universal law states that absolutely every object in the universe attracts every other object, right? So if you and your friend are just sitting next to each other on a bench, is there a gravitational force pulling you two together? And if so, why aren't you simply sliding towards each other? Well, let's actually apply the math to a real-world scenario. Let's say Mahendra, who has a mass of 75 kilograms, and Virat, who is 80 kilograms, are sitting exactly 1 meter apart. If we apply Newton's law using the universal gravitational constant g, we can calculate the exact force acting between them. The result? It's a tiny, tiny 4.002 times 10 to the power of -7 newtons. And this perfectly explains our everyday reality. Because that calculated force is so exceptionally small, the normal everyday friction of the bench easily stops Mahendra and Virat from moving. Now, if that bench were completely frictionless, with 0 initial velocity, they actually would start moving towards each other. But in our practical world, friction definitely wins that battle and holds them firmly in place. Next up, section 3, the physics of ocean tides. You all must be familiar with the high and low tides that occur in the sea, right? The seawater level naturally increases and decreases twice a day at regular intervals. Well, as you can see perfectly illustrated here, these huge oceanic movements are actually a direct consequence of the gravitational force exerted by the moon on our planet. So let's break down the mechanism. The water mass that is situated directly under the moon experiences a very strong pull towards it. This gravitational attraction naturally causes the water level to bulge upwards, creating a high tide right at that specific location. At the exact same time, the places on Earth situated at 90 degrees from that high tide experience a minimum water level, giving us our low tides. It's just a beautiful rhythmic cycle driven entirely by gravity. Let's transition to section 4, Earth's gravitational pull. We know the Earth attracts every object near it. And since the Earth's center of mass is right at its core, this gravitational force is always directed vertically downwards. But this leads us to a very famous paradox. If the Earth's gravity is pulling on both a falling apple and the orbiting moon, we have to ask ourselves, why does only the apple fall straight down to the ground? This brings us to the brilliant concept of orbital mechanics. You see, Earth's gravity is constantly acting on the moon, exactly like it does on the apple. The big difference, the moon possesses a very specific, continuous velocity along its orbit. It's this continuous horizontal speed that keeps the moon perpetually falling around the Earth rather than crashing straight into it. If that orbital velocity suddenly disappeared, the moon, and honestly all our artificial satellites, would just drop straight down to the Earth. Now for section 5, calculating gravitational acceleration. According to Newton's second law, any force acting on a body results in acceleration. In our case, we call this the acceleration due to gravity, denoted by a small g. The math here is really straightforward. We simply equate Newton's second law, where force equals mass times acceleration, with his universal law of gravitation, where force equals g times m over r squared. The mass of the falling object, small m, neatly cancels out on both sides. So we're left with acceleration g, equating to the gravitational constant g, multiplied by Earth's mass m, divided by the radius r squared. Now, if our object is sitting exactly on the surface of the Earth, that small r simply becomes capital R, the radius of the Earth. By plugging in our standard values, so g is 6.67 times 10 to the power of -11, Earth's mass is 6 times 10 to the power of 24 kilograms, and the radius is 6.4 times 10 to the power of 6 meters, we can easily calculate g. It comes out to be exactly 9.77 meters per second squared right here on the Earth's surface.
And our final topic, Section 6, why gravity varies slightly.
So as you probably know, the Earth isn't a perfect sphere. Because it's rotating, it actually bulges slightly at the equator and flattens out at the poles. Because of this, the distance from the center is actually smallest at the poles, which makes g highest there at about 9.832 meters per second squared. Conversely, it's lowest at the bulging equator. Furthermore, as we gain altitude, the distance r increases, which means g naturally has to decrease. Now, this decrease is pretty negligible if you're just flying in an airplane at 10 kilometers up, but it becomes a very significant drop when we're talking about artificial satellites orbiting way above the planet. As we wrap up our explainer today, I want to leave you with a fascinating thought experiment to really ponder over. Look back at the formulas and concepts we've just discussed and ask yourself, what exactly would happen to our universe, to the moon's orbit, or even to the ocean tides if gravity just suddenly vanished? Or imagine how completely different the cosmos would behave if the universal constant g miraculously doubled in value. I want you to think critically about these scenarios, students. Until next time, keep exploring and keep learning.